Good day, everyone. Today we're going to have modeling with higher order differential equations. So we will be having the applications for second and higher order differential equations. Now, for linear models, we will be using initial value problems to solve applications in mechanics and in circuit analysis. In this section, we are going to consider several linear dynamical systems in which each mathematical model is a second-order differential equations with constant coefficients along with the initial conditions specified at time that we shall take to be t equal to 0. So initial conditions, the time would be initially set to 0. So the mathematical model for our linear differential equation would be A, second derivative of y with respect to t plus b, derivative of y with respect to t plus cy equal to g of t, where y of 0 is equal to y naught and y prime of 0 is equal to y sub 1. This would be our differential equation, and this would be our initial value conditions. The function g is called the driving function, the forcing function, or the input of the system. So this g of t would serve as the input to the system. So driving function, forcing function, or input to the system. If g of t would be set to 0, we're going to say that the system is free or unforced. A solution y of t of the differential equation on an interval I containing t equal to 0 that satisfies the initial condition is called the response or output of the system. Let us first consider the spring mass systems for free and damped motion. Newton's second law. When a mass m is attached to the lower end of a spring of negligible mass, it stretches a spring by an amount s and attains an equilibrium position at which its weight W is balanced by restoring force Ks of the spring. As indicated in the figure, the condition of equilibrium is mg equal to Ks or mg minus Ks equal to 0. So we can imagine that initially, if there is no mass, we will be having the natural length of the spring. However, when we apply a mass to the spring, like in this case, it would be stretching the spring to a certain distance. Let's have it as a distance x to the spring. So this is the elongation of the spring. After elongating the spring to a certain distance, it would follow or it would experience the spring's elongation. So that would be equal to K times S. So Hooke's law states that the force on the spring is directly proportional to the elongation of the spring. So the force on the spring is directly proportional to the elongation. Hence, F is equal to Ks, where K is the spring constant. Assuming that the weight the spring neutralizes the weight, so we have weight equal to the force on the spring. So the weight, which is equal to mass times acceleration due to gravity, is equal to Ks, the force on the spring. That is why we will be having the equation mg minus Ks equal to 0. Take note that this is the equilibrium condition. But what if we're going to apply a force to this spring? So say for example, we're going to pull this downward or push it or just apply a certain force to the spring. And then after that, we release the body or we release the block. With that, we will be having vibrations on the spring. So suppose that the mass on the spring is set in motion by giving it an initial displacement, an elongation, or a compression. And an initial velocity. So any of this or a combination of this, initial elongation or compression and initial velocity, upward or downward. Let us assume that the motion takes place in a vertical line, that the displacements x of t of the mass are measured along the line such that x is equal to 0 corresponds to the equilibrium position. So take note, the equilibrium position is at the point where mg is equal to ks, and that the displacements measured below the equilibrium positions are positive. So take note of this convention of signs regarding motion and displacements. Downward is positive and upward would be considered negative. So this is our equilibrium position, and a movement or a position downward would be considered positive, and a position upward will be considered negative. To construct a mathematical model that describes this dynamic case, we employed Newton's second law of motion. The net or resultant force on a moving body of mass m is given by the summation of forces equal to mass times acceleration, wherein we are going to define acceleration as the second derivative of position with respect to time. So we define velocity as the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. So thus, acceleration is the second derivative of position with respect to time. If we further assume that the mass vibrates free of all other external forces, so we consider it as a free motion, then the Newton's second law gives the motion m times a is equal to negative kx plus s plus mg, which is equal to negative kx plus mg minus ks. So take note that this is equal to the force on the spring, while this is the weight. So this is the total elongation. The elongation due to the weight, which is x, and the elongation of the spring due to the motion, so that would be s. So we will be having negative kx, kx is the elongation and s is the elongation due to the weight. So we will now be having negative kx plus mg minus ks. This is what we have set to be equal to 0 earlier. Mg minus ks. This is the equilibrium state, mg minus ks, which is we have set earlier to be equal to 0. So thus, we have m, second derivative of x with respect to t, equal to negative kx. If we transpose this, it would now be m x double prime plus kx equal to 0. So this is a second order differential equation. The first term f sub 1, which is equal to negative k times x plus s on the right-hand side of the equation 1, is the restoring force of the spring. The negative sign indicates that the force acts opposite the direction of motion. So the spring is pulling the object upward. That is why it is negative. And the weight, which is mg, is pulling the object downward. So that would be a positive force. Now let us have the differential equation for the free and damp motion. By dividing 1 by the mass m, we obtain the second order differential equation, second derivative of x with respect to t plus k over mx equal to 0. So take note that we have just divided the entire equation by m. So this seems to be y double prime plus a constant times y equal to 0. So with that differential equation, we can solve this one using the homogeneous equation. So we just first let k over m to be equal to omega squared. So we set omega squared to be equal to k over m, such that it would now be, so this equation, k over m, would now be equal to omega squared. And thus, we will be able to solve the differential equation for this harmonic free and damped motion. So this is a simple harmonic motion or free and damped motion. Two obvious initial conditions associated with this are x sub 0 is equal to x naught and x prime of 0 is equal to x sub 1. This refers to the initial displacement or the initial position and the initial velocity of the mass. So this is the initial position and the initial velocity. So thus, the resulting equation would be, so here we will be having omega squared is equal to k over m. So omega is equal to square root of k over m. So the resulting differential equation would have its auxiliary equation m squared, so second derivative m squared plus omega squared equal to 0. So the auxiliary roots would be plus or minus omega I. So plus omega I and negative omega I. This would give us a solution which is equal to, so for imaginary roots, we will be having sine and cosine. So thus, from the form y is equal to c1 e raised to alpha x cosine beta x plus c2 e raised to alpha x sine beta x, we have alpha to be equal to 0, the real part is 0, and beta is omega. So thus the solution is x of t is equal to c1 cosine omega t plus c2 sine omega t. The period of motion described by this is t equal to 2 pi over omega. The number t represents the time, so period, no? So that would be the time it takes for the mass to execute one cycle of motion. So this is a sinusoidal curve. So it is a periodic motion. So the period would be the time it takes to complete one cycle of motion. So the frequency of motion f is equal to 1 over t. So that's the reciprocal of 2 pi over omega. So thus, we have omega over 2 pi. And is the number of cycles completed each second. For example, if x of t is equal to 2 cosine 3 pi t minus 4 sine 3 pi t, so we have 3 pi t as the argument for the trigonometric function. So the period is 2 pi over omega. So 2 pi over 3 pi or 2 over 3 seconds. And the frequency is 3 over 2 cycles per second. So for every second, there would be 1.5 of the graph being formed. So for a graphical viewpoint of the graph of x of t, it repeats every 2/3 second. So meaning after 2/3 second, it would just be the original graph. So x of t plus 2 over 3 is just the same as x of t. And 3 over 2 cycles of the graphs are completed each second. Or equivalently, 3 cycles in the graph are completed every 2 seconds. The number omega equal to square root of k over m is called the circular frequency of the system. Finally, when the initial conditions are used to determine the constants C1 and C2, we say that the resulting particular solution or response is the equation of motion. For example, let us consider this case. A mass weighing 2 pounds stretches a spring 6 inches. At t is equal to 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4 over 3 foot per second. Determine the equation of motion. So basically, we're looking for x of t, which is the equation of motion. For our solution, we must first identify that there must exist a constant unit of measurement. So we are given with 6 inches, 8 inches, and 4/3 foot per second. So everything must be converted into a similar unit of measurement. So first, we convert 6 inches into 1/2 foot. While 12 inches is 1 foot. So 6 inches is 1/2 foot. And 8 inches is 8/12, which is 2/3 foot. In addition, we must convert the units of weight given in pounds into units of mass. So the 2 pounds must be converted into the unit of mass, which is 2/32. So that would be 1/16 slugs. So with this, we must write the formula m x double prime is equal to mx double prime plus kx equal to 0. So the mass is 1/16 slugs. So that is 2/32. So that is 1/16. And k is, so since we have force, is equal to kx. And the force is 2, equal to k times 6 is 1/2. So k is 4. So we have this equation. So ma, so mass is 1/16. Acceleration is the second derivative of position with respect to time, equal to negative kx. So negative 4 times x. So with this, we can have omega squared equal to 64. So omega is 8. The initial displacement and initial velocity are given as 2/3 and negative 4/3. So it was pulled at a position of 8 inches. So 8 inches is 2/3 foot. And x prime is negative 4/3. Take note that it was stated that it would be given an initial upward velocity. Upward is negative in our sign convention. So now, omega squared is equal to 64 and omega is equal to 8. So the general solution of the differential equation is now x of t is equal to c1 cosine 80 plus c2 sine 80. Now let us apply this initial condition. X of 0 is equal to 2/3. With that, the equation of motion would be if we would be applying a t is equal to 0, so we would be having 2/3 is equal to c1 cosine 0 plus c2 sine 0. Cosine 0 is 1, sine 0 is 0. So c1 is 2/3. Now, if we're going to differentiate this, so we will be having x prime is equal to negative 8c1 sine 80 plus 8c2 cosine 80. So we apply the condition negative 4/3 is equal to negative 8c1 sine 0 plus 8c2 cosine 0. Cosine 0 is 1, sine 0 is 0. So C2 is negative 4/3 all over 8. So this is negative 1/6. So this is your C1 and this is your C2. So we have our solution to be x of t equal to C1 cosine 80 plus C2 sine 80, which is now x of t is equal to 2/3 cosine 80 minus 1/6 sine 80. Now, there is an alternative way of writing this. That is, when we combine the cosine and sine, the sum of cosine and sine, into a single function. So when C1 is not equal to 0 or C2 is not equal to 0, the actual amplitude of A of the free vibration is not obvious from the inspection of the equation. So the amplitude of the equation is very, very significant in the equation of motion. So this is the extent to which the object moves. So we need to identify the amplitude of the motion. So for example, the mass in example 1 is initially displaced 2/3 foot beyond the equilibrium position, and the amplitude of vibration is a number larger than 2/3. So what we're going to do is to apply our knowledge in trigonometry. So it is often convenient to convert a solution of form 3 into a simpler form x of t is equal to the amplitude A sine omega t plus some phase difference phi, where the amplitude A is equal to the square root of C1 squared plus C2 squared. So something similar to the Pythagorean theorem. And phi is the phase angle defined by sine phi equal to C1 over A, and cosine phi is equal to C2 over A. And thus, tangent phi is equal to C1 over C2. To verify this, we expand 6 by the addition formula of the sine function a sine omega t cosine phi plus a cosine omega t sine phi. So we have a sine phi cosine omega t plus a cosine phi sine omega t. So sin cos cosine. It follows that from this figure, if phi is defined by sine phi equal to C1 over A and cosine phi equal to C2 over A, then we have a triangle with the legs C1 and C2 and the hypotenuse A. So sine phi is C1 over A and cosine phi is C2 over A. So then this becomes A C1 over A cosine omega t plus A C2 over A sine omega t, which is now your C1 cosine omega t plus C2 sine omega t equal to your equation of motion x of t. In view of the foregoing discussion, we can now write the solution in 5 in the alternate form x of t equal to a sine omega, which is 8t plus phi. Computation of this amplitude is straightforward, so that is the square root of c1 squared plus c2 squared. So that is the square root of 2/3 squared plus negative 1 over 6 squared. So that is 4 over 9 plus 1 over 36. So that would now be square root of 17 over 36, which is approximately equal to 0.69 foot. Now this is bigger than the original displacement, 2/3 feet. But some care should be expressed in computing the phase angle. So in trigonometry, we have the two quadrants where angles would just be the same. So if you have computed for tangent, quadrant 1 and quadrant 3 would have the same sign. Quadrant 2 and quadrant 4 would have the same sign for the tangent. So if we're going to solve for phi, so C1 is equal to 2/3 and C2 is negative 1 over 6. So tangent phi is negative 4. So that is C1 over C2. So 2/3 over 1 over 6. So 2/3 times negative 6 over 1. So that's negative 4. Now, inverse tangent of negative 4 is negative 1.326 radians. This is not the phase angle, since arctangent of negative 4 is located on the fourth quadrant and therefore contradicts the fact that sine phi is greater than 0 and cosine phi must be less than 0. Since C1 is greater than 0 and C2 is less than 0. So we're going to find the equivalent angle for negative 1.326 radians. So we add pi. So it must be a second quadrant angle. Quadrant 2 and quadrant 4 would have the same sign for tangent. So we have pi is now equal to 1.816 radians. So thus, we can now write the equation of motion x of t to be equal to a sine omega t plus phi. So it would now be square root of 17 over 6 sine of 80 plus 1.816. The period of this function is 2 pi over omega, so 2 pi over 8, which is the same as pi over 4. For our graphical interpretation of motion, so initially, the object is pulled two-thirds of its position, and then it follows sinusoidal function. So it would move into a sinusoidal motion or sinusoidal form. Take note that this is the positive value and this is the negative value. So reading from left to right, the first 5 positions marked with the block dots corresponds to the initial position of the mass below the equilibrium position where x is equal to 2 over 3. The mass passing through the equilibrium point or the equilibrium position for the first time heading upward at x is equal to 0, the mass as its extreme displacement above the equilibrium position, which is the amplitude negative square root of 17 over 6, the mass at the equilibrium position for the second time heading downward at x is equal to 0, and the mass at its extreme displacement below the equilibrium position at the amplitude square root of 17 over 6. The black dots on the graph given in the figure also agree with the 5 positions just given. So this is the initial position, the point where x is 0, the one of the critical points, another value where x is equal to 0, another critical point. So this is negative square root of 17 over 6, the amplitude of the motion. And then it would now be a continuous periodic function. Note, however, that in figure 5.1, the positive direction in the tx plane is the usual upward direction, and so is opposite to the positive direction indicated in the figure. Hence, the solid blue graph representing the motion of the mass in the figure is the reflection through the t-axis of the blue dash curve in the figure. Form 6 is very useful because it is easy to find values of time for which the graph of x of t crosses the positive t-axis. We observe that, so when is the sine function 0? So we just set sine equal to 0, and this is equal to the integral values of pi. So that would be for pi, 2 pi, 3 pi, 4 pi, and 5 pi. So this omega t plus phi would be equated to n pi for integral values of pi.